Okay guys, can you hear me now? Finally. Okay, good. Is everything good? Sound, volume, everything? Yeah, nice. It seems like I had some difficulty joining. Awesome. So, in today's contest, I didn't have a chance to participate, but I have read the problems. I solved the first few ones till problem E, but we will discuss the rest of them as well. We will discuss the solutions of the rest of the problems as well. So, some people cheated into this round. I'm good. I'm great. Thank you. How are you guys? How was your contest? Let me open the problems so that we can start discussing them. Okay, I see. What about the rest of you? I think everything should be ready now. You can't see my screen. It's weird. That's me. Okay, now you should be able to see my screen. Okay, shall we start discussing the first problem? Everything seems fine. All the angles, okay. We are going to discuss all the problem. There was a live stream during the contest? What do you mean? Okay, let's start talking about the first problem. Okay. This is the first problem, uploads more RAM. It says that you want to upload n gigabytes of RAM. Every second you will upload either 0 or 1 gigabyte of RAM. However, there is a restriction on your network speed. In any k consecutive seconds, you can upload only at most 1 gigabyte of RAM in total. Find the minimum number of seconds needed to upload n gigabytes of RAM. Okay. So let me move this. Okay. So about the first problem, this is the easiest problem in today's round. This problem, we want to upload n gigabytes of RAM, and every k consecutive seconds we can just upload 1 gigabyte. So what can we say? Well, in here I can just say that for each of the n minus 1 first gigabytes, I should spend at least k seconds. So I should spend n minus 1 times k seconds initially, because I send 1 gigabytes, then I should wait k minus 1 more seconds. Then I send 1 more gigabyte and I should wait k minus 1 seconds. And then after that, I need the 1 additional second to send the last gigabyte of RAM. Okay, so all the first n gigabytes, all the first n minus 1 gigabytes get a block of size n, but for the last one, I don't need to wait after sending. I mean, I just send it and I'm done. So the answer is n minus 1 times k plus 1. Okay. I'm originally from Iran, yeah. I'm from Iran. But right now I'm at University of Maryland. Okay, so is the problem completely Okay, is this problem fine? So the answer is just, if you want, I can also implement it very fast. I mean, it's just, let me maybe, sorry. Okay, I cannot submit code. I cannot submit code right now because it is being judged. So it's just, I see in n and k, and I see out n times n minus 1 times k plus 1. That's gonna be all. If you are okay with that, please use this emoji so that we go to the next problem. Otherwise, let me know to explain it again. Is it completely fine? Awesome. Okay, great. So let's now move on to the next problem. Case sorts. You are given an array of integers a of length n. You can apply the following operation any number of times, maybe 0. First, choose an integer k such that k is between 1 to n and pay k plus 1 coins. Then choose exactly k indices such that these indices are from 1 to n, and for each one of them increase them by 1. You want to make it non-decreasing. You want to find the minimum number of coins needed to make a non-decreasing. You have to say what is that minimum possible number of operations. Okay, so for this, thank you. For this problem, I can just say that I have n numbers, right? A1, A2 to AN. And all the values of AIs are up to 10 to the power of 9. Well, what can I say? I can just say that if I consider all the number, I can define some goal for each number. For example, I want to set that what I want each number to be. I know that for each AI should become equal to, if it is less than maximum of A1 to A of I minus 1, it should become equal to that maximum. So it's like for each AI, I can define B of I as maximum of A1 to AI. Then BI is my goal. BI is what I want to make this number into. So for each number, I have a goal. I say that my number is initially AI. I want to make it BI. Because I don't need to make it greater than that value, definitely, but I need to make it at least this much. Otherwise, it's not greater than or equal to all the numbers before it. Then, when I know all the goals, I can just see that how much I should increase each number. I should see what is BI minus AI. And this is definitely a non-negative number because BI is equal to maximum of A1 to AI. And then when I know all these numbers, I should just say that, well, first of all, I should increase each one of them this much. So I have this, and I have to see that what is the number of operations that I'm gonna have. Because in each operation, I have one additional cost for that operation. Other than having one cost for increasing each number, I have one additional cost for that specific operation. So the number of operations is going to be maximum of all the BI minus AIs. Because each time I can choose all the numbers which are greater than 0. If you define CI equal to BI minus AI, each time I can choose some of them such that their CI is positive, and I decrease the values of CIs by 1. So the minimum number of operations that I can have is going to be the maximum of all these CIs. So it's just enough to say that I can define these values of B's, And then I can just easily just say that it's enough to find the maximum of them and sum of them and add these two values, and this is gonna be our final answer. Is this one also clear? If you're okay with that, please again use this emoji so that we'll move on to the next problem. If anything is unclear, let me know and I will explain it again for you. Yeah, sure. Example. For example, consider the last example in the test cases is 3, 4, 4, 12, 37, 60, 3, 1, 1, 6, let's make it smaller, 6, 1, 3, and so on. Let me just write one more number, 6, 5, 3, 6, 5. So these are the numbers that I have. I just define b of I as maximum of all the numbers up to that number. B of 1 is going to be 3, 4, 4. B of 2 is also going to be 3, 4, 4. B of 3 is going to be 3, 4, 4, 3, 4, 4, 3, 4, 4. For this one, it's going to be 6, 13. For this one, is also going to be 6, 13. So B of I is the cumulative maximum up to that element. I know that for each one of these, I should make them into this goal. B of I is my goals, what my numbers should turn into. Then I can say that how much do I need to increase these numbers to get there. And I can say that my answer is going to be sum of those values I need to increase plus maximum of them, because the number of operation is going to be equal to maximum of all these values that I have. Because in each operation I can choose several of them. If the maximum is, for example, I don't know, for example, 10, I need 10 operations because each time I can decrease maximum by 1 only. So my final answer is going to be the sum of these values, because for each one of them I have to increase this much, and my cost will be increased by 1 whenever I increase any number. So my initial answer is going to be sum of all the values of CIs, but also I have to see what is the number of that operations that I'm gonna need. And that is going to be maximum of CIs, because I need at least that many operations in order to make my array A into array B. Does it make sense now? So the point is that, for example, in here, C of I is 0. In here, C of I is 344 minus 12. So it's going to be 332. For this one, it's going to be 307. For this one, it is going to be 284. For this one, it's going to be 33. And so on. For this one, it's going to be 0. And for this one, it's going to be some, I think 58, 258, I think. Right, 248. 248. Okay, so this is how much I should increase each of these numbers. First of all, I should sum up all these values, because for each one of them, for each one of these elements, I have to increase that element this much. But also, I have to have several operations. In each operation, I can choose several one of them. And each operation by itself has one additional cost as well. So I need to see that what is the maximum of all these values. For example, in here, the maximum value is 332. I should also add 332 to this final answer, because I need at least 332 operations in order to make 12 into 344. So I can say that my answer is going to be the sum of these values plus the maximum of them, because I need at least that many operations. I know that each operation has one additional cost. It is going to be equal to length plus 1. So there's that I want to see that what is that plus 1s. I want to minimize that plus 1s. The minimum of that plus 1s is equal to maximum of CIs. Does it make sense now? If you're okay, please again use this emoji. if you're okay, we can move on to the next problem. Awesome. Okay, awesome. And guys, also if you like the videos and the live streams, I would appreciate it if you like the video or subscribe to the channel. That would definitely help us. And also, if you want to be part of our community, you can join our Discord server, which is the pinned message. Okay, so let's move on to the next problem, problem C. Basil's garden, it says that there are n flowers in a row. The number I of them is has initially a positive height of h sub I meters. Every second, the wind will blow from the left, causing the height of some flowers to decrease. Each time I can say that if h of I is greater than h of I plus 1, the value of hi will change to maximum of 0 and hi minus 1. So for each one of them that its height is greater than the height of the next one, its height will decrease, but it never becomes negative. So I have maximum of 0 and hi minus 1. You have to say how many seconds will pass before hi is equal to 0 for all I from 1 to n. Okay. So let's discuss this one. Well, my idea for this problem was to use dp. I'm saying that, okay, I have these values of h1 to hn. I can just say that I can define dp of I as the number of seconds that it takes till flower number I will have height 0. Okay, so dp of I is the number of seconds it takes so that the height of flower number I will be 0. Well, first of all, I can just say that I argue that if flower I's height becomes 0, before that, flower number I plus 1 should have its height equal to 0. So before height of flower I becomes 0, the height of flower I plus 1 should become 0. Because otherwise, I will not decrease this one from 1 to 0. Because before it becomes 0, it becomes 1. And all of them are initially at least 1. As you can see in here, all the HIs are at least 1 initially. So I can just say that when I change it from 1 to 0, the next one, h of I plus 1 should be less than hi if I decrease h of I from 1 to 0. So h of I plus 1 should be 0. So first of all, I say that the term that I make h of I equal to 0, before that h of I plus 1 should be 0. So the first fact that I say is that dp of I must be greater than or equal to dp of I plus 1 plus 1. I can see that how much does it take so that flower number I plus 1 becomes 0. And then I say that I need at least one more operation. It is greater than or equal. I think you cannot see this color. Let me change this color. To this. So dp of I must be greater than or equal to dp of I plus 1 plus 1. But also dp of I should be greater than or equal to h of I as well. Because each time its height will be decreased by 1, and I need at least hi seconds for that. Then I say that these two conditions are enough, and dp of I is indeed equal to maximum of hi and dp of I plus 1 plus 1. dp of I plus 1 plus 1 and hi. I say that dp of I is equal to this. Why? Because if both of them happen, if height of I, I know that in the previous step, height of I plus 1 has turned into 0. So I have no problem to make this one 0. But there's also a possibility that the height of this one is way greater than the height of the next one. In that case, the height of I does not turn into 0 exactly the next time that height of I plus 1 becomes 0. They never become close. So when they are never close, each time height of I will be decreased by 1. So it takes exactly hi steps, hi turns for flower number I to have height 0. So what I can say is that my dp of I is equal to this. This way I can calculate all the dp's, and the maximum of all these dp's is going to my equal to my answer, which is dp of 1 always. The dp of first one is the maximum dp and is going to be our final answer. For example, if you consider the first test case, dp of the last elements is 2, because it takes 2 steps to make this 2 into 0. For this one, it is going to be equal to maximum of dp of I plus 1 and height of itself, which is 1. Maximum of 3 and 1 is 3. So this one is going to be 3. For this one, it's going to be maximum of dp of I plus 1, which is 4, and height of itself, which is 1. Maximum of is 2 is 4. So the answer for this one is going to be 4. For this example, the latest example, for this one, dp is 2. For this one, it's maximum of its height and dp of I plus 1. So it is going to be maximum of 3 and 3, it is 3. For this one, it's going to be maximum of 3 plus 1, which is 4, and 4, which is 4. For this one, it's going to be dp of this one plus 1, which is 5, and height of itself, which is 4, so it's going to be 5. For this one, it's going to be maximum of 5 plus 1 and 7, so it's going to be 7. So the answer of this one is 7. So dp of I is equal to maximum of dp of I plus 1 and hi. And at the end, I should see out the dp of the first elements. If this one is also clear for you, please use this emoji. If it is not clear, just tell me to explain it again. Yeah, the intuition is that the main fact is that if I want flower number I to become 0, before that, flower I plus 1 should become 0, right? Before flower I becoming 0, flower I plus 1 should become 0. So the first thing I say is that dp of I is greater than or equal to dp of I plus 1. That's one thing that I know for sure. dp of I should be greater than or equal to dp of I plus 1 by 1. This is if flower number I plus 1 should turn in. I know that because dp of I plus 1 should become 0 before dp of I, before height of the flower I can become 0. But also, each flower has some heights, and if the height of the flower number I is way greater than the height of flower I plus 1, I know that this one is not an issue. I plus 1 is not an issue. My main issue is that the height of this flower is too long. So if it is hi, if the height is hi, it takes exactly hi steps for it to turn into 0. So I can say that I compare these two. I say that first, dp of I should be greater than or equal to dp of I plus 1, but also it should be greater than or equal to hi. And these two things are enough. I mean, either these values are close to each other or they're not close to each other. If they are not close to each other, it's going to be hi. If they are close to each other, then this one should wait for the next one to turn 0 first, and then it can become 0. So dp of I, therefore, is going to be maximum of these two cases. Either it's going to be dp of I plus 1, I plus 1, or it's going to be hi. Does it make sense now? Well, when I saw the problem, it gave me the feeling of dp, because each one is so dependent on the next flower. Each flower is so dependent on the next flower, right? Because of that, it gives me some feeling that if I want to find out the answer for flower number I, the answer of flower I number I plus 1 is going to help me. Therefore, it gives me some intuition of dp. That's okay. I need to somehow consider I plus 1 as well. dp of I represents the number of turns that it takes, the number of seconds that it takes until flower number I has height 0. Okay, and then I said that dp of I definitely should be greater or equal to dp of I plus 1 plus 1, and also dp of I should be greater than or equal to hi. So, and these two conditions are enough, so dp of I is equal to maximum of dp of I plus 1 and hi. Okay, does this make sense? I wrote it in the chat, so if you're seeing the video in the right hand side, you can see the chat. This is how I calculate it. Okay. So, shall we move on to the next one? Ans equal to maximum of ans and ai. Yes, you're right. You're right. You're right. This also works. Yeah. If it also works, if we say that, that was very cool. It also works if we say that the answer is equal to maximum of all ai plus i's. Excuse me. Sorry. All ai plus i's. This also works, yeah. For each I from 1 to n. That's basically the same thing. It's like we see that which flower is our bottleneck, which one is the most problematic one. And we can say that, we can see that how much it takes for that flower to become 0. And then it takes I additional steps to make the previous one 0 as well. So yes, this would also work, because it's just like I say that at the end I'm gonna have some chain. Okay, consider the latest flower, the leftmost flower, that its height does not turn into 0 right after the next one. Okay, for example, this is flower number I. Its height does not turn into 0 right after flower number I plus 1. So I know that it takes hi. Let me, instead of ai, use hi here, because I always used hi in the explanation. So it takes hi seconds for this one to become 0. And this was the latest flower that does not, its height does not turn into 0 right after the next one. So all the ones after this, their height will become 0 exactly right after the next flower. So before I have I flowers before this one, I have h0 to h of n minus 1. I use 0-based indexing. There are exactly I flowers before this one, so it takes exactly I additional steps for the previous one to become 0. This is the same as our dp. We are doing almost the same thing as our dp. You can see that our dp also calculates this, because each time it's increasing the values one by one, and when it sees a better h, it will update the value of h. So RDP also is calculating this. But yeah, this was also a correct approach. You could just say that this is the answer is equal to maximum of hi plus I for all the i's. Yeah, heights are not 0. The heights are all initially at least 1. That's why I emphasized on this. All hi's are at least 1 initially. And that is so important. Height is not initially 0. Okay, so does everything completely make sense? Awesome. So, no problem. So, if only I step is required for making previous ones 0. Yeah, I will upload videos on DP for sure. Yeah, sure, I will repeat it, because I said that I is the leftmost flower I is the leftmost flower that does not turn into 0 right after the next one. So I know that all the flowers after it, exactly after their next flower, they will become 0. So I assume that I is the flower number I is the flower that does not turn that does not turn into 0 right after the next flower. So I know that all the flowers in here turn into 0 right after the next flower. So assume that I call a flower good if right after I plus 1 turns 0, right after that I turns 0. And I call it bad otherwise. I call it bad otherwise. So if right after the next flower it becomes 0, I say it is good, otherwise I say that it is bad. And the point is that if when this one is the last bad flower, all the next flowers should be good. So they will become 0 right after the next flower. So if this is the last bad flower, I can just say that it takes hi seconds for this one to become 0. And then right after that, all these I flowers will each step one of them turns 0. So my answer is going to be hi plus I. Is it clear now? Does it make sense? If it makes sense, please, again, use the same one. And if any part is unclear, just let me know. The approach leader is the last number that had all numbers after this to be less than itself, and then add. Why is strictly less than itself? It doesn't matter if it is because the number of them is also important. For example, if you have a 5, but then you have 1,000 ones, even though this one is 5 and the next one all 1, but it takes so many steps that until you can turn this one to 0. So you can't just consider the numbers themselves. What are those heights? You should also consider that how many of them you have. Yeah, for sure. I will definitely make a guideline video for pupils. I already have made a video for newbies, what they should do and what they shouldn't do, but for sure I will make video for pupils as well. Okay, so shall we move on to problem D? Problem D is also an interesting problem. It says that Alice and Bob are playing a game. Initially there are n cakes with the cake number I having a tastiness value of a sub I. Alice and Bob take turns eating them. Alice starts first. Each time Alice should eat a cake that its tastiness is strictly greater than the maximum tastiness of any of the cakes she's eaten before that. But Bob can choose any cake that he wants. And at the end, the game ends when the current players can't eat a suitable cake and let X be the number of cakes that Alice ate. Then Alice wants to maximize X while B wants to minimize X. Find out how many cakes Alice will eat if both players play optimally. N is up to 5,000 and also all the AIs are up to N. Well, let me tell you about my idea on this problem first. When I saw this problem, I was thinking about DP. Again, in this problem, I also had the feeling of DP. You know, the tastiness of the cakes are from 1 to n. First, let's compress all the numbers and remove all the numbers that there's no such cake with that tastiness. For example, if we do not have any cake of tastiness 5, we will remove 5 and we will shift everything to left. Okay, I can easily do that, right? I can just see that in the worst case scenario, I can have a vector of all the tastinesses, and then I can say that I can just, for each value AI, I can compress this vector, unique this vector, and then I can say that AI is equal to lower bound of AI in this vector. Then the tastiness of, if I have k different tastinesses, all the tastinesses will be from 1 to k, or 0 to k minus 1, if I use zero-based indexing. So what I'm saying is that Bob, it's like Bob wants to block the maximum number of values. I mean, Bob needs to, what do I mean by blocking a value? For example, assume that we have 3 and we want to block 3. It means that Bob should eat the maximum number of cake number 3s, so that Bob should eat all of them, so that Alice can never eat this cake. I know that the answer for Alice is at most k, because we have k different tastinesses of cakes. So Alice's answers cannot be greater than k. And it is exactly k minus the maximum number of cakes that we can block. We need to see that what is the maximum number of cakes, what is the maximum number of tastinesses that we can block. We can stop, we can eat all of them, Bob can eat all of them, so that Alice do not eat any of them. So we need to see that what is the maximum number of cakes that we can block. And in order to find that out, I can just say that I can define dp of I, which says that assume that you're Bob and Alice is now eating cake number I. And I definitely there's an important thing as well. I definitely know that Alice needs to eat cakes in increasing order. I mean that if there is any cake remaining of tastiness 3, she will never eat a cake with tastiness 5. That doesn't make sense, because it's like she's losing tastiness 3 and 4. But she could eat that. Even if she has saved 5, even if this was the last cake with tastiness 5 and she has saved 5, but the point is that she's losing 3 and 4, which doesn't make sense. She's losing 2 cakes, or at least 1 cake, even if she saves one other cake, but she's losing another cake tastiness. So that doesn't make sense. Do you agree with that? Do you agree that Alice should always eat the cake with minimum possible tastiness? Minimum possible tastiness greater than her last move. Awesome. So we know this. Now dp of I says that if now it's Alice's turns and Alice is eating a tastiness, a cake with tastiness I, then what is the maximum number of cakes that I can block? Well, I can say that when I assume that I have calculated dp of I. Assume that I have calculated dp of I start from the end, from dp of, for example, k, and assume that I have it. For example, I know that dp of k is 0, because if Alice is eating cake with tastiness k, there are no remaining cakes afterwards, so there's nothing to block. So dp of k is 0. Now assume that I know dp of I and I want to update all the previous dp's of j's. I need to find out if it makes sense for me to block cake number I. Block cake number I itself. Well, the point is, assume that we have ci cakes, we have cnt of I cakes with tastiness equal to I. Assume that we have cnt of I cakes with tastiness equal to I. It means that if I want to block tastiness equal to I, if I want to block that, Alice should have at least cnt of I cakes here. Alice should have at least cnt of I cakes here, so that she would eat one by one, and after that I will eat one cake with tastiness equal to I, such that when Alice reaches I is blocked. I doesn't have any cake anymore. So what I can say is that if I have any j such that j is less than I minus Cnt of I should say that I should maximize dp of j with dp of I plus 1. Do you agree with this? So all I'm saying is that if there's some j before this one, if there's some j such that I can say that the distance between j and I is greater or equal to greater or equal to Cnt of I have enough space to eat this cake. All the cakes with this tastiness. So then the answer, then I should increase the answer. Do you agree with this? So the point is that I need to increase the answers of those ones. I need to say that their dp should be increased this way. Also, there's just one important thing in here. The point is that if there's one other thing that I should consider, and that is that if I minus j is greater than Cnt of I, not only I can eat all the cakes of with tastiness equal to I, but also I can eat several additional cakes with other tastinesses after this, such that the next time I can just block those numbers as well. So if I have some remaining steps as well, I can block the next numbers too. So this gives me the intuition that I should add another additional dimension like rem. It says that how many I have remaining. dp of I and rem means that Alice is going to eat cake number I, but I have rem additional steps. I have rem additional steps for Bob, that Bob can eat any of the cakes after this. So the point is that when I want to see, when I have, for example, dp of I and j, I and, for example, rem, I know that I know that when I want to block cake number I need to have at least Cnt of I steps. So the previous time, I should, when I consider that I have some j in here, let's for a second assume that j is fixed. Let's assume that j is fixed. I know that when I was in j and Alice was eating cake number j, cake with tastiness j, I should have at least dp of j, and my remaining steps should be at least this rem that I have for I, because in here I should have at least rem remaining, plus j I minus j minus Cnt of I. This is the distance between I and j. This is the number of turns that it takes from Alice to eat all the cakes in this period, to eat all the cakes in this period. And I know that whatever Cnt of I is, if Cnt of I is less than this value, then it means that I have several more additional moves as well later. But if it is less than that, it means that I should spend some of this RAM. Does it make sense? Is it clear what I want to do? So I want to store, in another dimension, I want to store that what is the remaining number of steps that I'm gonna have. okay, I'm gonna store that. What is the remaining steps for Bob? For example, Bob has some additional steps that Alice has ate something, but for Bob we haven't chosen yet that which cake it should eat. In our strategy, we haven't chosen yet that which cake it should eat. So we can spend it later on. So it says that I should see that what is the value of rem in here. So whatever the value of rem is, I should have it in here as well. And from rem, I know that I should have at least this much more because I have to spend this much. Or to be more precise, I think I should subtract this one because the sign should be negated. Because this is the distance, these are the steps that I'm gonna have. This is the steps that I'm gonna have in here. And this is what I need. So if what I need is more than the distance, then I should spend some part of the remaining there. So in my dp of j, the remaining should be more. So this initially gives me an O of n cubed solution. This initially gives me an O of n cubed solution, and now I tell you that how to optimize it. But for now, I have a dp of O of n to the power of n cubed solution. If you are okay with that, for now, I haven't finalized it yet. If you are okay with that, for now, please use this emoji. Has anyone also used the same approach? So, yeah, dp of I and j means that Alice is going to eat the cake with tastiness I, and j steps, and I know that for Bob there are j steps that I haven't decided yet that which one of the cakes Bob wants to eat there. So it's like I have j additional steps to eat for Bob. I can choose any cake and eat j of them. I have j additional steps for Bob. It means that they were j steps that Alice has ate something, but I haven't decided yet for Bob to which one to eat. So it's like there are some additional tokens. It's like there are some additional, let me share this. It's like I have some additional tokens for Bob, which means that Alice has ate something. Bob hasn't decided which one to eat. In our strategy, we haven't decided yet. In that situation, what is the best thing that Bob can do? So we just store that, okay, this is what remains for Bob, and we can choose it whenever we want. So rem is just like additional tokens that Bob has, and we can say that when we have this rem, I know that I should go to some j for some j if Alice is going to eat cake number j now. I know that how many cakes it should eat. It should eat exactly I minus j till it gets here. So it takes at least I minus j steps. So if I minus j plus rem is the tokens that Bob already has. I minus j is the additional steps that it takes Alice to eat these new cakes. So Bob can eat from the cakes of tastiness I in those steps as well. So if this value is greater than or equal to CNT of I, it means that Bob has the chance to eat all the cakes with tastiness I when Alice comes here. When Alice gets to eat cake number I. If this was greater than this, it means that we can block I. So if this happens, it says that we can block I, because I minus j steps it takes from Alice to eat all the cakes from j to I minus 1. Also, I had remaining additional tokens that Bob can eat freely. If some of them was greater than or equal to CNT of I, it means that until Alice gets here, Bob can eat all of these cakes, so it can block I. This is the second dimension of my DP. I will store this. And rem is also up to n, definitely. And then I say that, okay, I minus j plus rem should be greater than or equal to CNT of I. If that was the case, I need to see that what is rem minus this value. My remaining in there should be at least this much so that I can come here and my remaining becomes this. Okay. Does it make sense? And the point is, each time that I move j leftward, this value will change only by 1. Each time when I move j to the left one times, it's like I have one additional cake to eat. So the second dimension will change only by 1. And that gives me some structure. It's like I know that for each I, there is a specific value for the second dimension. That DP is important for me. And I can store this. I can store this, that what is this formula? I mean, it's like it is j, and this is something related to j, something that changes with j. Each time that I change j by 1, this one changed by 1 as well. So I know that there is some relationship between this and j, and I can store that, how that relationship works, and then I can say that those specific values should be updated using this DP of I and rem. And this way I have all the DPs, and at the end I need to know DP of 1 and 1. DP of 1 and 0, sorry. It means that Alice is going to eat the first cake, and for now Bob doesn't have any additional tokens to eat any cake. I have to find that out. So my optimization from O of n cubes to O of n2 is to just see that each time when I move j leftward, it's exactly like I have one more steps for I. So it's like in here I need one less value for the second dimension. My second dimension can be 1 unit less than before. So if for j I needed some value for rem like r1, r of j minus 1 is r of j plus 1, minus 1, r of j minus 1. Because whatever I needed to have remained in here, if Alice is going to eat this cake, it's like I have one more chance. So my remaining token can be one less. So it's like always the first dimension minus second dimension is a constant value. So I can say that I can easily update all such values, such that the difference between the first dimension and the second dimension is a fixed value. And I can update all of them. This way I can update them easily. I can just store that for each difference. What is the best DP that I can have, and I can easily calculate the maximum of them. And then I know that what is the maximum number of cakes that I can block. Does this make any sense now? Is it clear? Please, again, if it is clear, use this. If you used any other approach, you can also say that in the comments, and I can explain those approaches as well. But this was the approach that came to my mind when I saw the problem. If any part is not clear, just let me know. I hope that it made sense. Otherwise, we will move on to problem E. Okay, so let's move on to problem E now. Problem E. You are given a tree with n vertices rooted at vertex 1. If the vertex number I has an integer ai written on it, let L be the set of all direct children of V. A tree is called wonderful if the number of each vertex is less than or equal to the value of all its children. In one operation, you can choose any vertex V and increase A of V by 1. Find the minimum number of operations needed to make the tree wonderful. Okay, so in here, I just have a tree, and each time I can just choose I can just choose a vertex, and increase its value by 1, I want the value of the children, the sum of the value of the children, to be greater than or equal to the value of their parents. What can I do in here? Well, I can say that, first of all, if a of v was less than sum of its children, I can just make it equal to the sum of its children, and it will have no harm. It will make no harm if I make it. I mean, the operations doesn't make any issue. The operations for me do not make any issue if I use that, right? I think I need to let me see. I need to just make sure that my solution for this one is completely correct. But I'm saying that if a of v is less than this, the good news is that I can simply increase these values. Yeah, I can simply increase these values like a of v, spend 1 and increase them, and no issue will happen, because v is still okay with its children, and also v is going to be still okay with its parents if it was previously okay. So it doesn't cause any issue. So whenever we see that for some v, a of v is greater than the sum of the children, if we see that a of v is greater than the sum of the children, I need to increase sum of the children, and my priority should be to increase the children, I mean greedily increase the children which they're already less than or equal to their children. So because I said that these vertices, I know that for these vertices such that a of v is already less than or equal to the sum of its children, adding them does not cause any issue. So my first priority should be increase the children such that they are already less than the sum of their children. If they're already less than the sum of their children, by adding them, no issue will be caused. But what if there are no remaining such elements such that I can increase them? Well, the point is, if there are no remaining one of them, again, there are some of the vertices which are equal to their children. I know that we have fixed these ones, so they are also less than or equal to the sum of their own children. They are already fixed, so they are less than or equal to the sum of their children. If they are exactly equal, if nothing is less than its children, again, I can consider the children of its children. If I have a children of the children, a vertex that it is less than the sum of its children, then I can increase this one, and then I can increase this one by 1. So it's like it has cost of 2. So it's like if I can each time find out what is the vertex in this subtree with minimum possible heights, the vertex with minimum heights, such that I can increase its value. What does it mean that I can increase this value? It means that it is either a leaf. I know that I can increase the leaves and that doesn't cause any issue, or its value, the value of that vertex, let's show it with x, because v is my root of the subtree. There should be some x such that a of x is strictly less than sum of all its children. All of its children. Y is a child of x. So these are the vertices that I can add them, and whatever their height is, the cost of adding them is going to be the difference of their heights and the current vertex heights. The cost of adding them is their height minus the current vertex height, because I have to add all the vertices in this path, and then I have to add all the vertices in this path. So it's like for each vertex I can keep some potential which is equal to, if it is a leaf, its potential is infinity. I can add it as I want. If they are not, it's going to be a of sum of the children minus this vertex, sum of the children minus the vertex itself. It means that how much I can increase this vertex so that it is still okay with its children. Okay. And then each time I can consider the vertex its minimum height such that its potential is greater than 0 and increase the value. So I decrease their potential but increase the value of all the vertices in this path. And the cost of it is going to be height of x minus height of v. H of x minus h of v. So it's like I can just have a set for all these vertices. I can have a set of their potentials, and each time I just consider the vertex with maximum heights such that its height is with minimum height such that its potential is non-zero, and I increase that one, I decrease its potential then, and the cost is going to be the difference between their heights. This way I can have a greedy solution. Do you agree that this greedy solution will work? And because I haven't accepted this problem yet, has anyone used the exact same approach? Maybe you can define, yeah, d of u is exactly the potential. D of u, which is equal to a of u minus sigma of a of v, is the potential. Is it clear so far? If it is clear, please use this emoji. So all I'm saying is that I can define h of x. My answer will be increased by h of x minus h of v. So the only thing remains is that how to keep these sets. I have a set pair of heights. I have a set pair of heights of a vertex and potential of that vertex. And each time, and I know that I only store all the vertices such that their potential is greater than 0, is positive. And I say that each time I take the minimum one, the beginning of the set, and I will increase this one as much as I can, as much as there's some value that should be in this vertex needs some value. I need to calculate the minimum of potential of x and how much I need my value to be increased. And then either potential becomes 0 or my need will become 0 after each step. So I either remove one vertex from the set or my need becomes 0. So in total, it's going to be n operations in the whole tree, because each time either a potential of a vertex will become 0 or my need becomes 0. And how can I merge these sets? In order to merge these sets, I can use SAC, for example. I can use SAC, and I can see that when I want to merge two sets, I see that the size of which one is less than the other one, and I can just move all the ones in the smaller one to the ones in the bigger one. And this way, changing the positions in the sets is going to be n log steps in total, so my total time complexity would be n log squared of n. If you're not familiar with SAC, you need to first learn what is SAC, and then you can solve this problem with this approach. Although there might be other approaches as well. H of x is height of vertex x. Yeah. So is it clear? Has anyone also used SAC on this problem? Have you guys also used SAC on this problem? Or has anyone solved it with any other solution? You know what comes to my mind for solving this problem is using SAC. Maybe I can take a look at the codes of other people to see if anyone has also solved this problem. It's another solution. It is problem E. So what comes to my mind is that I need to store all the vertices, their heights, and the potential they have, how much they can be increased. so that it would make no harm to the tree. And each time when I need to increase some vertex, I need to find the vertex with minimum height such that I can increase this value. And then the cost of this operation is going to be equal to the difference between the heights of these two vertices. Okay, do any of you have any questions about this one? It might be another solution without SAC as well, because I'm taking a look at the codes of others, and I think there is a solution with without SAC too. But this was the solution that came to my mind. I recommend you to also read the text tutorial. Maybe they have a better solution as well. Yeah, sure. I will recap the solution again. I'm just saying that. Let me bring the iPad. Okay. So I'm just saying that for each vertex, if I see that I need to add something to their children, so assume that need is equal to sum of children, A of V minus sum of children of V. A of V minus the sum of children of V. So it means that I need to increase by this value. I need to increase the sum of their children by this value. I say that I have a set of all the vertices that I can increase their value by some amounts. And a vertex can be increased with no harm to the tree if and only if that vertex X either should be a leaf or A of X should be strictly less than sum of A of Y, where Y is a child of vertex X. So one of these two should happen. So for each vertex, I can store a potential. The potential for leaves is infinity because the leaves can be increased by any value. And that wouldn't cause any issue to the tree. But for all the other vertices, it's going to be the sum of its children minus the value of itself, how much I can increase it. So potential of X, if X is a leaf, potential of X is infinity. If A of X is less than the sum of the children, it's going to be sum of the children minus A of X. And in a set, I have a pair of potentials, heights and potentials, and each time I consider some vertex with minimum height such that its potential is not zero. And I see that what is its potential, I consider the minimum of the potential of this vertex and the need. And whatever this value is, let's call it val. I will increase all the vertices in this path by val. Then my tree is still good because this val is less than or equal to potential. And also need can be decreased by this value of val. So after that, I can say that potential of X will be decreased by val, and also need will be decreased by val. And because val is equal to minimum of these two, at least one of them becomes zero. So in total, the number of operations will be at most n, because each O of n. Because each time either my need is satisfied for a vertex or a vertex is removed from my set. And when I want to merge two subtrees, it's just enough to use SAC, for example, to merge them. And in order to merge them, I can just store the smaller one in the bigger one. This way, you can show that each vertex will change its place at most log of n times. Therefore, it doesn't change. I can also do it in an easier way. Now that I'm thinking, I can also do it without SAC. I can for each word, I can use the starting time and finishing time, maybe. No, I'm not sure about that. Yeah, I'm not sure about that. So yeah, my idea is a sec. It cannot be simplified like what I thought. But I think that there are also other solutions without sec. If you want, you can read them. Maybe if you want, we can take a look at other solutions as well. Do you guys want to take a look at other solutions too? Solutions without sec, or do you want to move on to problem F? Which one do you prefer? If you want, we can also take a look at other people's solutions. Okay. So if you are okay with that, we can move on to the next problem, problem F1. Well, problem F1 and F2 are both the same, only their constraints are different. This one, I have just read the problem. I haven't solved it. I just read it very quickly. And I didn't participate in the contest. So we are going to see the solutions to see how can we solve this one. And this is F2. You are given an array A of integers A of length n. In one operation, you can choose an index I such that I is at most size of A and set AI equal to I. And AI is equal to I, and we can remove AI and AI plus 1 from the array and concatenate the remaining parts. Find the maximum number of times that you can perform the operation above. When I read the problem, the first intuition that came to my mind was that maybe it's always the best to remove the last good pair, the last element such that AI is equal to I. But let's take a look at the solutions of F2. Let's see how people solve it. It's a very clean code. The code that they're using is a very clean code. I know that. I don't know why this happens. Okay, so I know that let's see that how this person has solved this problem. He gets the numbers. Okay, there's a 4 on I from 2 to n, and I each time will be increased by 2, and there's a 4L from 1 to L plus I minus 1 less than or equal to n. This condition seems like that it says that L minus A of L should be is greater than or equal to 0, and then L minus A of L is modulo 2 is 0. It means that this element can go to its position. I mean, if their difference is even, because each time you remove 2 elements from left, if the distance between an element and its correct position is odd, you can never get there, because each time 2 elements will be removed from its left. And if this element is not going to be removed. So in this case, we can just say that, I guess that it means if this element can be removed at some place, can get to its position at some place. And also, guys, if you guys have any solutions, you can say that as well. I mean, maybe instead of trying to understand the code, you can also share your solution with us. Maximum of f of L plus 1 and k minus 1 is less than or equal to L minus a of L divided by 2. So if this one is greater than this one, why he took maximum? Oh, I see. I think I'm understanding it. F of k plus 1 Well, what I understand so far is that if I have some, for each L and R, he wants to figure out how many steps, what is the maximum number of operations he can have in the range from L to R. And in here, he says that if f of L plus 1 and k minus 1 is less than or equal to L minus a of L divided by 2, it means that there are enough elements that we can remove from the left part so that this element goes to the correct position. Yeah. Well, it says that a of L is somewhere and wants to go to position L if it wants to get removed. If it wants to get removed, it has to go to position L. And then it says that consider this, we choose some k from L plus 1 to R, L plus I. If dp of, oh, if dp of I minus 1 was greater or equal to f of I and j, oh, oh, I guess that f of I and j means that if I want to completely remove this interval, if I want to completely remove the interval from I to j, then what is the minimum number of elements that I should remove from the left part of it such that I can do that. Let me just make sure and then I will explain on tablet. So f of I and j, the f of L and R, the objective is to remove everything from L to R. We want to remove everything from L to R, and we want to know that how many additional elements from the left of this interval should be removed first, so that this will be shifted leftwards, so that I can remove these elements as all completely. So it fixes the value of L, and it says that obviously this should be true. L minus A of L should be greater than or equal to 0, and this should happen if I want to remove L. Because if I want to remove this interval completely, at some step L should be removed. And it means that if f of L plus 1 and k minus 1, f of L plus 1 and k minus 1 is less than or equal to L minus A of L half. Oh. Is less than A minus A of L minus A of L oh, cool. Maximum of L minus A of L half f of k plus 1 and R minus k minus L plus f of k plus 1 and R minus k minus R L plus 1 I understood the general idea. I'm just trying to find this detail. This is problem F. Tutorials are also given. I can first explain this. I think I'm okay with explaining it. Yeah, tutorial is also given. But anyway, let me explain this to you. Okay, so let's again start. Yeah, let me start explaining this to you. What I understood from this solution. Okay, the problem was that you are given an array A of length n. In one operation, you will perform the following two-step process. Choose an index I such that ai is equal to I, remove a of I and a of I plus 1. Find the maximum number of times that you can perform the operation above. Well, I read this code and it says that f of L and R says that if I want to see that, first of all, I want to see that can I remove the interval from L to R completely or not? And if I can remove the interval from L to R, what is the minimum number of elements that should be removed from the left part of it so that this interval can be shifted leftward, so that I can completely remove the elements in this interval? So if f of L and R is 10 to the power of 9, 10 to the power of 9 is inf. It means that I cannot remove the interval from L to R at all. So f of L and R just says that can I remove all the elements from from L to R or not? And if I can, what is the minimum number of elements that should be removed from the left part of it so that I can remove these parts completely? And then it says that, okay, if I want to remove this part completely, at some point L should be chosen and should be removed with one of the other elements. Let's say that that element is K. So he says that, first of all, it only can happen if L minus A of L is greater than or equal to 0 and L minus A of L modulo 2 is 0. Because in here I have A of L. So if I want to remove L at some point, if I want to remove A of L at some point, it should go to position A of L. So first of all, A of L should be either equal to L itself or it should be somewhere such that its distance is even to this point. Its distance should be even to this point. Otherwise, there's no way that this element can go to A of L can go to the position of A of L so that it can be removed there. So only in this case, these dp's are valid. If so, I should define some R. R is going to be L plus I minus 1. I is the length of this interval. So this 4 is because he first has a 4 on the length, and then after having a 4 on length, he fixes L and R will be uniquely determined. And his intervals are closed. And then he have a 4, K from L plus 1 to R to fix that which elements will be removed with L. And K each time should be increased by 2 because this interval should be even because they will be removed 2 by 2. And now he wants to check if he can remove L and K with each other. He just says that f of L and R will be equal to minimum. It only can happen if f of L plus 1 and K minus 1 is less than or equal to L minus A of L half. Why? Because I know that when I want to remove L with this one, L can be shifted leftwards at most L minus A of L half times. Because if it will be shifted leftwards more than this, A of L will go to a position less than A of L. And then I can never remove that anymore. So I know that if L is going to be in a position that it can be removed somewhere, an operation can be on it somewhere, it should be shifted leftwards exactly L minus A of L half number of times. So this interval, its f should be less than or equal to this value. Because otherwise, if it's not, there's no way that I can first remove these ones and then remove L. So only this should happen. And then I say that f of L and R is equal to minimum of f and current value of f of L and R and maximum of L minus A of L half, because at the end I need at least these many elements to be removed from left so that A of L will go to the position of A of L. And f of L plus 1 and K minus 1, this was not needed really. Because I know that f of L plus 1 and K minus 1 is less than or equal to this. So this one is not really needed. And f of K plus 1 and R, which is this part should be removed afterwards, right? This part should be removed other than this part that is being removed. This part should be removed as well. F of K plus 1 and R so should be considered as well. And the point is that I subtract this value because I know that these values will be removed anyway. So I have the chance to remove these elements. So whatever they need, I have this many already. I have K minus L plus 1 half already that are removed. So whatever it needs, I can subtract this much because I have already removed them and the remaining should be removed from here. So it's very beautiful. So this is how I can calculate f of L and R. I can see that if I want to completely remove all the elements from AL to AR, what is the minimum number of elements that should be removed from the left parts so that this interval can be completely removed. And this way it can be calculated. Is it completely understandable? I can explain it once again on tablet as well. Let me explain it on tablet as well, once on tablet as well. Okay, it's not working. So, it's just saying that my pen is not working, so I should just, let me see. Okay, so f of L and R is defined as consider this interval. Yeah, sure, I will explain it again now. F of L and R is equal to all the elements AL to AR. Assume that I want to remove all of this. I want to remove all these elements. It says that how many elements from the left side of it, what is the minimum number of elements from the left side of it that I should remove if I want this interval to be removed completely. If I want to remove A of L to A of R completely, how many elements from the left side at least should be removed so that I can do that? Why do I need to remove some of the elements from the left? The reason is that maybe I need to shift this interval to the left a bit. I need to shift it to the left a bit so that the indexes will be in the correct places so that I have the chance of removing them. So for example, maybe A of L, for example, this position L is 5, A of L is 3. So at least 2 elements should be removed from the left side. I mean, you should at least remove 2 elements from the left side so that these will be shifted to left such that 3 will go to position 3 so that I can remove L. So I mean that sometimes when you want to remove f of L and R, I mean remove all the elements from L to R, from A of L to A of R. If you want to remove all of them, maybe you need some of the elements from the left side to be removed first so that you can shift these ones to the left so that their indexes will be correct and you can remove them afterwards. I mean that can only happen if L minus A of L is positive, non-negative, if L minus A of L is non-negative, because this element is right now at position L, but it should go to position A of L. For example, it is right now at position 5, but it should go to position 3 so that it is in the correct position. So L minus A of L should be greater or equal to 0, and it also should be divisible by 2. It should be even, because each time it can go leftwards by 2. So if it is not even, it can never get to the correct place. So these two, both of these two should happen. And then if it is so, I can say that, okay, there is a way to move the A of L to its correct place, to position A of L. A of L should go to position A of L, such that its position is equal to its value. So it is possible to do that. Now I can fix that. What is K, such that K will be removed with A of L, so that A of L and A of K will be removed together. I know that before that, I need to remove all the elements in the middle here. All the elements in the here should be removed first, so that A of L and A of K will become adjacent, and I can remove them afterwards. I know that in order to be able to have an operation on A of L, I need to at least shift these values. I mean, there should at least happen L minus A of L divided by 2 operations to the left, and not more than this. If more than this happens, A of L will go to the left of the position of A of L, and therefore it can never get to the correct position anymore. So I know that exactly these many operations should happen when I want to choose A of L. So first of all, I can say that f of L plus 1 and K minus 1 cannot be greater than this. It should be less than or equal to this. Otherwise, it means that in order to remove these parts, we are going to need more elements to be removed from here. And if we remove more elements from here, then A of L cannot ever get back to its correct position. So f of L plus 1 and K minus 1 should be less than or equal to this value. This is a condition that we have. Also, if you consider from a of k to a of k plus 1 to a of r, these elements should be removed with each other as well. And I know that f of k plus 1 and r is something. This problem is problem f2. F of k plus 1 and r is something as well. I know that whatever it is, I know that these elements all can be removed. These elements can completely be removed because I can remove the middle ones first and then remove the necessary ones from the left part and then remove L and R, L and K. So I can remove this if I want. I can remove all the elements in here. And if I remove them, K minus L plus 1 divided by 2 elements will be removed. So whatever f of k plus 1 and r is, I already can remove this much from the left of it. So I can subtract this, and if this was a positive number, it means that I still need additional elements to remove from the left side. So if I want to see that how many elements do I need to remove from the left side, it's going to be maximum of these two values, L minus a of L half, so that L will go to the correct position, and f of, for that specific k, f of k plus 1 and r minus k minus L plus 1 half, because these many elements, these many operations will happen here, so these are done. So whatever I need, I already have these many. So I need to see how much this is. So I need that many additional operations to happen in the left side. So the operations, the minimum number of operations that I need in the left side is equal to maximum of these two numbers. And then I have f of L and R for each L and R. And then I use a dp, and for each f of L and R, I know that how many operations I need from the left side of them, so that I can completely remove this part. Then I can start from the beginning and update all the dp of i's, because for each interval I know that if I can remove this with these many elements that have been removed so far, or I cannot. So dp of I is the maximum number of operations till I at the end. First of all, I can say that dp of I is equal to maximum of dp of I and dp of I minus 1. So because basically whatever I could remove previously, now I can remove them as well. And then I can have a for on all the intervals starting from here. And if this dp was greater than or equal to f of this range, I can update dp of j with dp of I plus this interval divided by 2. Because I can have these many additional operations for here to remove all the elements in here. So this is going to be all for this problem. This was very beautiful. I really liked the solution. This was very beautiful. There is another interesting problem named Zuma that is somehow similar to this one, but it's very simpler. This problem, let me send it to you in chat. If you want, you can think on this problem as well. Let me also show it on this problem, Zuma 607b. This problem also is somehow similar to this one, but way easier, but it uses the same core idea. Is it clear? I hope that it makes sense now. It was very enjoyable. I mean, the solution, I really liked the solution. This was a very beautiful DP. Yeah, sure. I will also send you the submission. I will also link that in the description below of the video. Let me send you the code. And thank you, Flamir, whatever his ID is, for this beautiful solution. This was very interesting. I really personally enjoyed this solution. So yeah, I hope it has helped you. I think for solving G1 and G2 it can take a lot of time. If anyone needs it, maybe I can make a video of it whenever I could. But for now, I guess because F took this much time, I think G can take more time as well. Is there anyone who needs problem G to be solved as well? I don't understand. DV and do you meant me? Did you meant me? If there is anyone, is that okay if I make a video for them later? I can try to make a video for those two problems, G1 and G2, and problem H later and upload them if anyone needs it. And thank you very much for watching the stream so far. I hope you have enjoyed and learned something. Sorry that it took time from you to solve the problem F2 at the end. I'm sorry for that, and I hope that it is still was beneficial for you. I really enjoyed the last problem F2. Thank you very much. Thank you very much. Thank you very much for watching. It was really great to have you again here. I love to see you in the streams. Thank you for watching. And I hope that I can see you very soon. Thank you very much that you're joining the streams. Goodbye.